Hi everyone, it's Japoo, and today we're going to be talking about definite use substitutions. So as always, the worksheet that I'm about to do and its answer key are linked in the description below if you would like to follow along. And today we're going to be talking about definite use substitutions, or definite use subs. If you're unfamiliar with use subs, I would definitely recommend, or if you want to just like brush up on U subs, I would definitely recommend first watching our indefinite use substitutions video. That'll help you a lot in understanding like what a U sub is, and it'll help you a lot on this worksheet as well. Before I get to any problems, I'm going to highlight the two most common mistakes that people tend to make when dealing with definite use substitutions. The first one is a mistake that's made for both like indefinite and definite use substitutions, and that's choosing the U. Sometimes it's a little tricky to figure out what your U is supposed to be. And so I really recommend kind of approaching a U substitution problem, especially one that's a little more complex, as choosing the U as something whose derivative is a part of the problem as well. Using that mentality might help you when choosing which part of the function is the correct U sub. And of course, we have problems on this worksheet where we are going to have a little bit of a difficult time kind of choosing the use, like what to make as the U, but following this mentality really helps. The second most common mistake is forgetting to change all of our x values to U values. Since we are doing definite U substitutions in this worksheet, we do have values on our integrals. And so in the problem, we're given x values on our integrals. And since we're doing U substitutions, we have to change those x's to u's. The way to do that is actually to plug in the x value into our chosen U, and then whatever we get from that will be our new U value. I did make a mistake when I was writing this video. When I was plugging in values into my final answer, I should have been plugging in U values, and I was plugging in the U value, but I labeled it as the X value. So just be wary of that. I did that for a couple of problems before I caught myself, and I will point them out when we're doing the video, but I just wanted to let you know ahead of time. This video is very long because U subs are hard. Indefinite U subs are a little tricky, and definite U subs are one more step after indefinite U subs because you have to plug in values after you get your U sub. It's a hard topic, and it's really important, especially for people who are taking the AB calculus exam or are in Calc 1 in college. But we have a lot of problems on this worksheet that will hopefully help you get familiar with U substitutions, definite U substitutions. So let's get started. I hope you guys brought snacks because this is going to be a minute. So the first thing that you really want to do with any U substitution problem is find your U. For number one, it's pretty straightforward. Our U is going to equal x minus 1. So then we have U to the 9, U to the power of 9. And then our du is just kind of whatever else is left. And in this case, all we have left is dx. So du equals dx. And that's really nice. When your du just equals dx, you don't have to do any kind of like equation manipulation, which we will have to do in later problems, and I'll show you that. But for now, let's just be thankful that we have a super simple one. So what we want to do after we get our U is change all of the x's to u's, right? So since we are given x equals -1 in the original problem, we're going to plug in -1 to our U. So our new value will be -1 minus 1, and that's -2. And we do the same thing for 1. We plug that into this U equation right here. So 1 minus 1 equals 0. And so those are our two new integral values. So those are the two things that we're going to put on our new integral. So now we're writing our new integral. And as you can see, I've replaced the previous x values. I replaced the 1 and -1 with 0 and -2. And then we're going to go ahead and substitute our u for x minus 1. As you can see, we have u to the power of 9. And then we substitute du for dx. So there are no more x's in our integral. And we're just going to forget about x's altogether. We're on to u's now. So now that we have all of that, we're going to take the antiderivative of our new u integral. And so according to the power rule, our antiderivative is going to be u to the power of 10 over 10. Just a little refresher on what the power rule is when we're taking antiderivatives or we're taking integrals of functions. The power rule is the old exponent of the integral plus 1. So as you see here, we had 9. That was our old integral, our old power, and we added 1 to get 10, and then divide that whole thing by the new exponent. So originally we had u to the power of 9. We added 1 to that exponent, so we got u to the power of 10. Divided by that new exponent, got u to the power of 10 over 10. Now that we have our antiderivative, we're going to plug in our new u values, and we're going to have, which are 0 and -2. So here's where I actually made my mistake. Instead of writing u equals -2 here, I wrote x equals -2. That's incorrect. This x right here should be u. I didn't switch up the values or anything. This -2 is correct, this 0 is correct, this just should be a u. So it's just a notation error, but since making sure that we've switched all of our x values to u values are super important when we're doing definite u substitutions, I just wanted to emphasize that. Anyway, now we're going to plug in our values to our u. We're going to plug in our u values to our u, and we'll get 0 minus -2 to the 10th power, to the power of 10 over 10. And just a reminder, this is kind of like an easy way to remember the powers of 2. I don't know if you guys know that game 2048 where you like slide like kind of blocks or whatever different ways, and you basically just like, it's powers of 2, so like 2 and 2 is 4, and then you get 4 and 4, 16. But that's an easy way to kind of remember the powers of 10, so, or powers of 2. So if you're kind of like remember the order that they go, 2 to the power of 10 is going to be 1024. And that's going to be over 10. And so our final answer is going to be -102.4. So this one was pretty straightforward, not too complicated. And the next one is pretty straightforward as well. So first what we're going to do is find our u. Our u is going to be 7 plus 2x. And our du is going to be everything else that's left over. So actually, in this case, our du is 2 times dx. All right. So we're going to keep going, and we actually want to rearrange the du equation so that we isolate dx, because what we're trying to replace, right, is dx in this case. We're not trying to replace a 2, because du is basically the derivative of the u that we did. So the derivative of 7 plus 2x is going to be 2 times dx. We don't have a 2 in this equation. We only have dx left. And so we're going to isolate dx, so we get du over 2. And that's what's going to go into our new integral. So just watch. I'm going to go ahead and write an empty integral. So I'm not putting any values in it yet. And I'm going to go ahead and write my u substitution. It's u to the 1/2. And then as you can see, I replaced my dx with du over 2. And I just went ahead and took that 1/2 out of the integral to make it a little less complicated when I'm trying to take my antiderivative. So I have 1/2 integral u to the 1/2 times du. And now what I have to do is find my u values from my original x values that I was given in the problem. So I have x equals 1, and if we put that into our u, we get 7 plus 2 times 1, which is 9. And then our other x value is 9. Put that into the integral. 7 plus 2 times 9, 7 plus 18 is 25. Those are our new values on the integral. So we're going to go ahead and take our antiderivative of this integral, since we have all of our components converted to u's from x's, and we forget about x's. So what we have, it's another power rule. Add 1 to the original exponent and then divide by the new exponent. And that's going to give us 2/3 u to the 3/2. And we're going to plug in 25 and 9. Again, I wrote by accident x equals 9. That x should be a u. It's u equals 9 because all of our x values have been changed to u values. I'm going to just cancel out the 1/2 and the 2 from the 2/3 to make my life a little bit easier when I'm plugging in. And then I'm going to go ahead and plug in my u values, which will give me 1/3 times 125 minus 27. Just a reminder on how to deal with a fractional exponent. What you want to do is deal with the bottom number first and then deal with the top. So the bottom number is a 2. So technically it's u to the 1/2, which means the square root of u. So when we're plugging in, let's say 9, we're going to have 9 to the 3/2. So we're first going to take the square root. We're going to deal with the 1/2 portion of that exponent. So we get square root of 9 is 3, and then we're going to cube it. We're going to deal with the top portion of that exponent. So 3 cubed is 27. You do the same thing for 25. Square root of 25 is 5. 5 cubed is 125. So that's how we get those two numbers. And then we're just going to solve and simplify. And that gives us 98 over 3. All right. Number 3 is where it gets a little more complicated. And that's because it's a little confusing to figure out what exactly our u value is. So if we look at this closely, we can actually see that if we take the derivative of this value right here, we would get 3x squared plus 6x minus 9, right? And if we took a 3 out of that, we would get 3 times, in parentheses, x squared plus 2x minus 3. That's this value right here. So the derivative of this part of the function is already in the problem. And that's going to mean that this part of the function right here is going to be our u. So in this case, we're going to make our u x cubed plus 3x squared minus 9x because its derivative is part of the question. So if we take the derivative of that, we're going to get 3x squared minus 6 minus 9. And then we're going to isolate, and then dx times dx, obviously. First, let me just go ahead and write down our u portion, our u substitution, since we've already decided what we're going to substitute. We're just going to have a u squared, right? And then the parts that I'm underlining are the parts that we want to make equal to du. So we're going to kind of manipulate this du equation so that we get x squared plus 2x minus 3 times dx. And the way to do that is just divide that expression by 3. So what we're going to get is x squared plus 2x minus 3 times dx equals du over 3. So that's why I put a 1/3 out in front and I just put a du. I replaced all of those other x's, the dx and the x squared plus 2x minus 3 with the du and the 1/3. Then we're going to convert our x values on our integral to u values by plugging it into our chosen u, plugging the x values into our chosen u. 0 cubed plus 3 times 0 squared minus 9 times 0 is 0. And 1 cubed plus 3 times 1 squared minus 9 is equal to -5. So those are our two x values on our integral. And now that we've completely substituted u's for all of our x's, we can go ahead and take the antiderivative of that integral. So we have another power rule in this case, and what we're going to get as our antiderivative is u cubed over 3, right? Add 1 to our old exponent 2 to give us 3, and then divide by that new exponent 3. And then we're just going to bring over that 1/3 that we already put in front of our integral to the next part of our equation. So this is our final kind of antiderivative right there. And then again, this number right here, or this letter right here, should be a u, not an x, because we have changed all of our x values to u values. And now we're going to plug our new u values into our antiderivative. And that's going to give us 1/9, because 1/3 times 1/3 is 1/9, times -5 cubed minus 0 cubed, which is going to give us a final answer of -125 over 9. Now we're going to move on to number 4. Number 4 also looks a little bit tricky, and it might be difficult to decide what part of the function we want to make our u sub. But if we remember our derivative rules, the derivative of ln of x is actually 1 over x. So since the derivative of ln of x is already in the question, we kind of get the hint that we should make our u ln of x, leaving our du, our derivative of u, to be 1 over x times dx. So if we're kind of constructing our u variable now, we're going to replace our ln of x, the thing inside the sign, with u, and then replace 1 over x and d of x, or dx, with du. Now our final step for completing our u substitution is to change all of our x values on our integral to u values. So we're going to make x equals 1 into u equals 0, because if we plug in 1 to ln of x, we're going to get 0, because ln of 1 is equal to 0. And if we plug in e to the power of pi into ln of x, we're actually going to get pi, because ln of e to any power is equal to just that power. The ln and the e cancel out. So those are our new values on our integral. And now we're going to take the antiderivative. So the antiderivative of sine is just negative cosine. And we're going to plug in pi and 0. Again, I accidentally wrote that x equals 0, but it should be u equals 0. My notation is incorrect. We have gotten rid of all of our x's and changed them all to u's, and pi and 0 are u values. So now we're going to plug those in to our antiderivative, giving us negative cosine of pi minus negative cosine of 0. Negative cosine, cosine of pi is -1, and cosine of 0 is +1. So that's going to give us negative -1 minus -1. And you can go ahead and cancel all of those negatives and minus signs out. And our final answer is going to be 2, because 2 positives equal, or 2 negatives equal a positive. 2 positives also equal a positive, not a negative, in math at least. Number 5, again, it might be a little tricky deciding whether to make 5x, or making x squared our x, or 5x squared our u. But we're actually going to go ahead and make x squared our u, because the derivative of x squared is 2x, and we actually have x already in the problem, right? So since the derivative of x squared is already in the problem, we're going to make x squared our u. So then our derivative, our du, is going to equal 2x times dx. Substituting our u's for the x's in the problem, we're going to get 5 to the power of u, and then to replace x and dx, we're just going to put du over 2. So we're going to put that 1/2 in front of our integral because we wanted to isolate x and dx to replace them with like our du value and whatever numerical values with that. So we're going to get 1/2 an empty integral because we haven't created our u values from our x values yet, and 5 to the u times du. Now we're going to find our u values from our given x values. So we're going to plug into 2x squared. So u equals 2 squared, which equals 4. And then we're going to do the same thing with 0. U equals 0 squared equals 0. So those are our 2 new u values. And now we can take the antiderivative of 5 to the u. So remember that this is not power rule, it's a different rule. Since our variable is technically the power, it's a numerical value to the power of our variable. So we're going to move our 1/2 over from outside of our integral. We're just going to bring that over. And the antiderivative of 5 to the power of u is 5 to the power of u over ln of 5. So that's going to be our antiderivative in this case. It's not the power rule, be careful with that. And we're going to plug in our u values that we found. So we're going to plug in 4 and 0. Again, I made a little bit of a notation error. I wrote x equals 0. It should read u equals 0, because we have replaced all of our x's with u's. We're forgetting about x's now. Okay, then we're going to plug in our u values to our antiderivative to get our answer. We're going to have 1 over 2 times ln of 5 on the outside equals, and if you remember FTC, it's top minus bottom. And this is kind of the first, I think, time in this worksheet where parentheses are especially important. Or I guess not, but just remember, I guess parentheses are always important. But kind of see that we're doing like 5 to the power of 4 is our top, and 1 to the power of 4 is our bottom. so be careful with that. All right, so we're going to keep going. Oh, that's supposed to be 1 to the power of 0. Okay, this is why I was confused. This is supposed to be 5. This is 5 to the power of 4, right? Because we kind of took out 1/2 and ln of 5, 1 over ln of 5, and we put that in the front. So now all we really have is 5 to the power of u. So we're going to plug in our top. We're going to plug in 5 to the power of 4 because our top is 4. And that's going to be 625. And then we're going to plug in our bottom, which is 0. So this should actually be 5 to the power of 0, I believe. And that's going to equal 1. So that'll give us 625 minus 5 to the power of 0, which is 624, and then we put that all over 2 ln of 5. So just remember our FTC rules, top minus bottom. That got a little mixed up there. I hope I explained that okay. If you have questions, you can always leave a comment on this video and we can, we'll answer it the best we can. But that 1 to the power of 4, I believe, should be 5 to the power of 0. We'll just keep moving on. Moving on to number 6. This one looks a little bit tricky, but really all you have to do for your u is make it equal to the thing inside of the parentheses. So our u in this case is going to be equal to pi times theta. And it may be a little tricky to figure that out because you may be thinking, oh, there are 2 kind of components to this problem. So maybe tan of pi theta should be u or something like that. But if you remember your derivative rules, you'll realize that secant theta times tan theta is actually the derivative of secant theta. So the antiderivative of secant theta tan theta is just going to be secant theta. So we can actually just replace all of the things inside the parentheses with a u, and we'll get a very easy antiderivative if you remember your trig steps. So what we're going to have here is secant u tan u and then we're actually going to isolate our dx from our du situation, our d theta from our du equation to get d theta equals du over pi, which is why there's going to be a 1 over a pi in front of our integral, and then we're going to just replace the rest of it with du. Then we're going to find our u values from our theta values. I wrote x in this case because I was kind of thinking of like the rest of the problems and how the variable is usually x, but in this case it is theta, but it doesn't matter because you're replacing with a u. So x equals 1/3. If we plug that into, or theta equals 1/3, if we plug that into our u, pi times 1/3 is pi over 3. Pi times 1/6 is pi over 6. So pi over 3 and pi over 6 are our new integral values. And now we can go ahead and take the antiderivative. So what we're going to get is 1 over pi, just bring that over, times secant u, because the antiderivative of secant theta tan theta, or secant u tan u, is going to be secant theta, or in this case, secant u. Again, that theta right here, this should be a u because we have gotten rid of all of our thetas. We've replaced all of them with u's. We should only have u's moving this time forward. It's the same u values that we just found on the left side, or the right side, on this side of the page, right here. These are our u values. We found them already, right? And that's exactly what we're plugging in. So it's just a notation error. And now we're going to go ahead and plug in. So we get 1 times pi, or 1 over pi, times 2 minus 2 over square root 3. And I'll explain how we got 2 and 2 over square root 3. If you remember, secant is equal to 1 over cosine. So all of this is related to cosine. So all you have to do is plug in pi over 3 and pi over 6 to 1 over cosine u. That's basically the same thing as secant u, right? So cosine of pi over 3 is equal to, I want to say, 1/2. I mean, it's 1/2 because then you would do 1 over 1/2 because it's 1 over cosine equal to secant, and that'll give you 2. Same thing with 2 over square root 3. Plug in pi over 6 to 1 over cosine u. Because secant is equal to 1 over cosine. All right. For number 7, we're actually going to want to kind of rewrite the equation a little bit to make it a little more obvious about what our u is. So our new equation is going to read x to the square root of x times x to the negative 1/2, because the square root of x in our original is in the denominator, right? So to bring it up, we have to make it negative. And then the square root in exponent form is 1/2. So now that we have that, we can kind of look at it a little bit. And we'll see that the derivative of square root of x, like just regular square root of x, is x to the negative 1/2. So what we're going to do is make our u equal to square root of x. We're going to make our u equal to this square root of x right here, the one that the e is going to. Once we do that, we're going to take the derivative of that u, and the derivative of square root of x is going to be 1/2 times x to the negative 1/2 times dx. Then, if we isolate x to the negative 1/2 in dx, well, first let me write down our u's really fast. Let's write down what we have so far, which is e to the u. And then if we replace x to the negative 1/2 in dx, we want to isolate those two so we can figure out what to replace it with. We're actually going to end up replacing it with 2 times du. It's really important to rewrite this equation so we don't accidentally think that this square root of x in the denominator is another u. We don't want to write this problem as e to the square root of x over square root of x, because we might accidentally make it e to the u over u, because they're both kind of square root of x's. But when we rewrite it, we can kind of see that we actually need to get rid of square root of x because it's a part of the du. Now that we have that, we're going to go ahead and find our u values from our original x values. So we originally had x is equal to 16, the square root of 16 is 4, and the square root of 9 is 3. So 4 and 3 are our new u values. All right, now that we have that, we're going to kind of just bring our 2 over that we had in front of our integral. And the derivative, or the antiderivative of e to the u is just e to the u. So this is our new antiderivative. This is our antiderivative, 2 times e to the u. And then we're going to plug in 4 and 3. This x, again, is written incorrectly. It should be u equals 3 because we've gotten rid of all of our x's at this stage. So we should only be plugging in u values. 3 is the correct u value, but the x is incorrect. It should be u equals 3. So now we're going to go ahead and plug in our values. And that's going to give us 2 times e to the power 4 minus e cubed. And that's your answer. Number 8, we're going to first find our u. It's a little tricky again. I actually have another recommendation to help you find your u's. A lot of the time your u is going to be your inside function. It's going to be whatever is in the inside of a trig function if there is something inside of a trig function. So like in a previous problem we had sine times ln of x over x. ln of x was the inside function, right? And that was our u. So in this case, again, pi sine x is our inside function, and that's going to be our u in this case. So, oh, that's not supposed to happen. Let's rewind it a little bit. I think I meant to hit the play button. Hold on 1 second. Okay, so we can just stop here. But since we made pi sine x our u, our du is going to be pi cosine x times dx. We just took the derivative of sine. We can actually see that cosine is in our problem already, so this worked out great for us. So first we're going to substitute our u, which will give us sine of u. And then we're going to kind of rearrange our du equation to isolate cosine x times dx, which is what we're trying to replace. And we get du over pi. So we're going to put that 1 over pi in front of our integral, and we're going to put du at the end. So we've replaced the rest of the x's. Now we're going to find the u values from our original x values. So if we plug in 0 to pi sine x of 0 is equal to 0 because sine of 0 is equal to 0. Then we're going to have pi sine pi over 2, and that's going to equal pi. So those are our 2 u values, 0 and pi. So we're just going to write that on our integral, and we've officially replaced all of our x's in this case. And we're going to take the antiderivative. So we're going to move over that pi, and that'll give us cosine u. And there's a negative in front of the 1 over pi because the antiderivative of sine is negative cosine. Because what's the derivative of negative cosine? It's sine. Because the derivative of positive cosine is negative sine. So if we kind of flip-flop those negatives and take the derivative of negative cosine, we're going to get negative sine, which is positive sine. So now we're just going to go ahead and plug in our values. Again, that x right there should be a u. We have replaced all of our x values at this point. Everything should be u's. So what we're going to get is negative 1 pi over pi times cosine 0 minus cosine pi. Cosine of 0 is 1, and cosine of pi is negative 1. So we're going to get negative 1 over pi times 1 minus negative 1, which is just equal to 2. Move myself over here so we can see. And that's just going to equal negative 2 over pi. And that's our final answer. So just some things to remember from this page. I think the main thing that we got out of this is that when we're trying to find our u in more complicated problems like number 8, number 4, number 5, we have to look at the rest of the problem and see if one part of the problem's derivative is also in the problem. And that's kind of a really great tip on how to decide what part of the problem you want to make your u. And then another recommendation that I do have, although this is not an absolute rule, if you look at the inside function of trig functions, sometimes you might find your u there in that spot. All right, so moving on. I did want to mention something, even though, especially on the AP Calculus exam and in Calculus 1 in college, the majority of the integrals that you are given are u-subs, but sometimes they actually aren't. And it's important to be able to distinguish when you need to take a u-sub and when you can just solve an integral using another method. So for example, number 9, if you look closely at it, at first glance, it kind of looks like you need to do a u-sub, right? But if you look a little closer at it, you realize that you don't actually need to do a u-sub in this problem. This is a no u-sub problem. It's actually a problem where all you have to do is expand the function that you're given. And basically what I mean by that is you just have to multiply the square root of x by x and 2. So you just distribute the square root of x to both of those values, and then you can actually just take a normal antiderivative. So let's see. First, what we're going to do is draw our integral. We're keeping the same values because we're not doing a u substitution, so we're just going to continue to use x values, right? I forgot to draw an integral, but I'll draw it in a minute. But we are using the same values that we were given in the problem since we are not doing a u substitution problem. What we're going to get when we distribute the square root of x is x to the 3/2 because we add the exponents of both of the x's. So x to the 1/2 plus x to the 1 equals x to the 3/2. And then 2 times square root of x is 2x to the 1/2, right? And there's the integral. So once we do that, we can take the antiderivative of both of those things using the power rule, which will give us 2/5 x to the 5/2 plus 4/3 x to the 3/2. The reason that's 4/3 and not 2/3 is because we originally had a 2 in front of our x to the 1/2. So 2 times 2 over 3 is 4 over 3. Then we're just going to go ahead and plug in our two values because this is still a definite integral. So we still do have to plug in values to get our answer. So if we plug in 1 for both of our x's, we just get 2/5 plus 4/3, right? And if we plug in 0 for both of our x's, we just get 0. So the final answer is 26/15. The two things in our integral had nothing to do with each other. One was not the derivative of another. They were no way connected at all. And that's kind of how you know that we're looking at a problem that requires something other than u substitution. So be careful with those kinds of problems because you will get used to doing u substitutions when you see complex problems like these, and they might be trying to trick you, so just be careful with that. Moving on to number 10, this is a u substitution problem. So we will be finding a u and like doing all that stuff. So the first thing we're going to do is find a u. And we're going to go ahead and make our u x minus 1, which leaves our du to be equal to just dx. So if we put that into our integral, we're going to have 2, which we took out of the original integral. It's like right here. We just kind of moved it out into the front to make it easier on ourselves. So we have 2 integral. We're leaving that blank for now because we haven't found our u values yet. So we have u to the negative 1/2 times du, right? Now we're going to find our u values. So if we plug in 10 into our u, we get 10 minus 1, which is 9. And then we get 2 minus 1, which is 1. So 9 and 1 are our u values. So we can put that on our integral. And now we can take the antiderivative of u to the negative 1/2. This is just a power rule. We're just going to add 1 to the old exponent. So we're going to add 1 to negative 1/2, which gives us positive 1/2, and then divide by the new exponent. So dividing by 1/2 is the same thing as multiplying by 2, because when you divide a fraction, you multiply by its reciprocal. So we're going to get 2, which was our original 2 from outside of the integral, times 2u to the 1/2. And then we're going to plug in our u values. Remember, we're not using any x's, so we're going to use our new values of 9 and 1. So here I actually properly wrote the notation. I finally figured out that I was writing it wrong. And I wrote u equals 1. So as you can see, we're completely forgetting about all of the x values that we had. We're done with x's, and we're now going to plug in these u values into our u antiderivative. So that's just going to give us 4 times, so I took both of the 2's out that were in front of the u to the 1/2 and made that 4. And then in parentheses, I wrote 3 minus 1, because the square root of 9 is 3, that's top, minus the square root of 1 is 1, that's bottom. So top minus bottom, and that equals 8. This was a pretty simple u sub, nothing too complicated, and we'll go on to the next one. So this next one is also pretty simple. Our u is going to be 8 minus x, right? So we can go ahead and write that. And our du is going to be negative dx. The reason it's going to be negative dx is because we are taking the derivative of 8 minus x, and the derivative of the minus x is a negative 1. The derivative of 8 is just 0, so that's why there's nothing there for that. But that's the only tricky part. So we're going to put in our u, that's going to be 1 over u, and then we're going to replace the dx with a negative du. So I'm going to put the negative sign out in front of the integral, and then just times du. Now it's time to find our new values for u from our old values that we were given in the problem, our x values. And we're basically going to have x equals 2 becomes 8 minus 2 is 6, so u equals 6. And x equals 5 becomes 8 minus 5 equals 3, so u is going to equal 3. So once we figured that out, we can write it on our integral. So we're going to have 6 on the top and 3 on the bottom. And now we're just going to take the antiderivative of 1 over u. That's just the simple ln. So we're just going to have negative ln of u as our antiderivative. Very easy. And we're going to plug in 6 and 3 into that. Again, forget about x's now, we're into u's. And so we're just going to ignore all of the x's that we dealt with earlier and only deal with u's now. So our after we plug in our values, we're going to get negative ln of 6 plus ln of 3. And now we're going to use a logarithmic property. When you subtract logs, you can actually just go ahead and divide them if they're like the same logs. So since we have 2 ln's, and negative ln of 6 plus ln of 3 is just technically ln of 3 minus ln of 6. We can simplify that to ln of 3 over ln of 6, or I guess rewrite it. We can rewrite it as ln of 3 over ln of 6, which simplifies to ln of 1/2. And that's our final answer. Okay, now we're going to move on to number 12. This is a little bit more tricky because it might be a little difficult to at first figure out what your u is going to be. But if we look at it closely, we see that the numerator of this problem is actually the derivative of the denominator. So let's go back and see if we can see the problem. My hand isn't in the way. Okay. So the derivative of x plus e to the x is 1 plus e to the x, which is the numerator, right? So since the denominator's derivative is already in the problem, we're going to make the denominator our u. So x plus e to the x is going to be our u in this case. This means that our du is going to be 1 plus e to the x times dx, which works out perfectly in this case for us. We don't have to rearrange that equation at all because we see exactly what we're replacing with du. So I'm going to go ahead, draw my integral without any values, and substitute my u. So I'm substituting the x plus e to the x with the u, which gives me 1 over u, and then 1 plus e to the x times dx is substituted with a du. So now that I've gotten rid of all the x's in my actual expression, I'm going to change my x values into u values by plugging in the x value into my u. So I'm going to plug in first 2. I'm going to plug in the 2 into x plus e to the x, which gives me u equals 2 plus e squared. And then I'm going to plug in 1 into the u, which gives me 1 plus e to the 1, which is just 1 plus e. So those are my 2 new values. They look kind of messy, a little complicated, but just think of it as a numerical value and put that on your integral. Now we're going to take the antiderivative of 1 over u. It's a simple ln again, so that gives us ln of u as our antiderivative. And we're going to plug in 2 plus e squared and 1 plus e into that problem, right? Which will give us ln of 2 plus e squared minus ln of 1 plus e. And again, we can use that logarithmic property that lets us divide logs that we are subtracting, giving us ln of 2 plus e squared over 1 plus e. All right, moving on to number 13. This is again a little bit tricky because it looks like a u sub, but we actually can't take the u sub of this. We're not going to take the u sub. There is no u sub in this problem. No u sub. We actually have a case of a split numerator here. What does that mean? I'll tell you what that means. That means that we're actually going to split this fraction up into 2 fractions. We're going to split the numerator. Keep in mind that you can only split the numerator. You cannot split a denominator. So if we had 2x over 4 minus x, we cannot divide that into 2x over 4 minus 2x over x. But we can if the numerator is able to be split. Since we're splitting our numerator in this case, we can change that into 4 over 2x minus x over 2x. And then I already did some simplifying here to make it easier on ourselves later. I canceled out the 2 in the first fraction, giving me 2 over x. And I canceled out the x in the second fraction, giving me 1/2, right? And again, we're going to keep the same values on our integral because we are not doing a u sub. We are just using x's, so we can use the x values. So we're going to have 3 and 1 as our x values. And we're going to take the antiderivative of our new integral after we've split the numerator. So we're going to get 2 ln of x. I did forget to write the x next to the ln, but it is 2 ln of x minus 1/2 x. And we're going to plug in (3) and 1. And that's going to give us 2 ln of 3 minus 3/2 minus 0 minus 1/2. That 0 is there because the ln of 1 is equal to 0. So that's why we have a 0 there. And then our final answer will be 2 ln 3 minus 1/2. So we decided to split the numerator in this case because it gives us a very easy way to take the integral. As you can see, that was very straightforward. So be on the lookout for functions where you can split the numerator or you can distribute to expand your function to make it easier on yourselves when you are doing integrals. Number 14 is another U sub problem. Really, you must recognize that the derivative of inverse sine is 1 over square root 1 minus x squared. So you have to realize that this top numerator has a derivative that is the bottom. So since the derivative of inverse sine is already in the problem, we're going to make inverse sine our u. So that means that our du is going to be 1 over square root 1 minus x squared times dx, which is perfect because that is exactly what we need to get rid of in and replace with du. So I'm going to write an empty integral and replace my u at the top. So I'm replacing sine, inverse sine of x, and then I'm just going to multiply by du, because du is equal to dx times 1 over square root 1 minus x squared, meaning it replaces all of that. Now we just have to find our u values from our original x values. So the first value that we have is square root of 3 over 2. The sine of square root of 3 over 2 is equal to pi over 3. So that means that the inverse sine of square root 3 over 2 is going to be equal to pi over 3. I switched that. The sine of pi over 3 is going to equal square root 3 over 2. So sine parenthesis pi over 3 close parenthesis is equal to square root of 3 over 2. So the inverse sine of square root 3 over 2, the inverse sine parenthesis square root 3 over 2 close parenthesis is equal to pi over 3. The same exact situation is happening with 1/2, which is our other x value that we have to change into a u value. The sine of pi over 6 is equal to 1/2. So that means that the inverse sine of 1/2 is equal to pi over 6. So our two new values are pi over 3 and pi over 6. Once we have that, we can actually go ahead and take our antiderivative, which is going to equal u squared over 2. And that's just a power rule. We add 1 to the exponent, the old exponent, so 1 plus 1 is 2, and divide by the new exponent. So we have u squared over 2. And then we're going to plug in pi over 3 and pi over 6. This is just going to give us pi squared over 9 over 2 minus pi squared over 36 over 2. So watch how I wrote this. I was really careful with my parentheses when I was writing it, and I really recommend that you are too, to make sure that you understand exactly what you're writing, and that whoever is grading your work understands exactly what you're writing as well. We can then go ahead and simplify that to pi squared over 18 minus pi squared over 72, which is eventually going to equal pi squared over 24 if you simplify enough and do some math. Just trust me on that one. If you want to check me, feel free to do so, or else we can move on to the next problem after I write pi squared over 24. So I did want to mention before we started number 15, sometimes the u that we choose is actually equal to the equation of a line. It's in the mx plus b format. For example, number 1, the u that we chose was x minus 1, and that is in that mx plus b format. M is equal to 1 and b is equal to negative 1. We have a similar situation in number 2. The u that we chose was 7 plus 2x. If we rearrange that equation, we get 2x plus 7, which is also in the mx plus b format. M is equal to 2, b is equal to 7. We have similar cases in problems 6, 10, and 11. And when you have easy u-subs like this, you actually don't even have to do a u-sub. You can multiply by the reciprocal of the derivative of the inside, which will just be a number. And I know this sounds a little confusing, but let me give you guys an example to try and help you think about it a little more. So say we had an integral of cosine 2x. So cosine and then in parentheses 2x. And we want to take the integral of that to find the antiderivative. So you might be thinking, oh, I'll just do a u-sub. And you could just do a u-sub. You could set u equal to 2x, and then just continue on as we've been doing this entire sheet. However, if you look at the inside of cosine, if you look at 2x, 2x is just a line. So if you multiply by the reciprocal of the derivative of the inside function, or the function that you would have set equal to u, then you actually get the antiderivative without even having to do a u-sub. So if we wanted to take the integral of cosine of 2x without doing a u-sub, here's what we'd do. We would first just go ahead and take the antiderivative of the normal, like how we would normally do it. So we would get sine of 2x. So the antiderivative of cosine 2x is sine 2x, right? That's pretty straightforward. Just some trigonometry, reverse derivatives, however you want to think about it. And then all we'd have to do is multiply by the reciprocal of the derivative of 2x. So you just multiply by 1/2, right? Because the derivative of 2x is 2. And then the reciprocal of 2 is 1/2. So your final answer, your final antiderivative for the integral of cosine 2x is equal to sine 2x times 1/2. So that's what I meant when I said that we want to multiply by the reciprocal of the derivative of the inside function, or the inside expression, or the expression that you wanted to set equal to u. Because that expression is in the format of a line. It's in the format of the equation mx plus b. So your derivative of that u is always just going to be a numerical value. It's always just going to be the m, if you think about it. Because the derivative of mx plus b is equal to m. Because b will become 0 when you take the derivative of it, and mx will just become m. Once you get good at u-subs, you can skip the u-sub altogether and just kind of use this process instead. We do have a quick calculus lessons series on our channel, and one of those videos is about skipping easy u-subs. And I really recommend that you go and check that out if what I'm saying is a little confusing. However, in number 15, this next problem, we're also going to practice this process. Notice we are never going to write u in this problem, and we're actually going to try and circumvent using u by thinking of the inside expression as a line. So notice that this function is a piecewise integral because f of x is a piecewise function. Sometimes on the AB calculus exam, you're going to get a question like this as a free response question. Because it's pretty involved, it does take a little bit of thinking, but if you know what process you have to follow, it's not too bad. What you're going to do is split up the integral based on where the function splits, and then solve from there, and then solve each integral individually. So if we look at our piecewise function, we see that the integral is going to split at +1, right? That's what this says, or the function is going to split at +1. That's what this says right here. And our function is going from -1 to 4, right? So we're going to have one integral going from -1 to 1 and one integral going from 1 to 4. How do we decide which integral goes with which function? Well, since e to the negative x plus 1 is for anything that is less than or equal to 1, that one is actually going to be in our integral that goes from -1 to 1. If we look at the other one, x plus sine pi x over 4, that function is for whenever x is greater than 1. So that's going to be in our integral that goes from 1 to 4. So first, let's just write that out. So from -1 to 1, our function will equal e to the negative x plus 1 times dx. And then from +1 to 4, our function is going to be x plus sine pi x over 4. And as you can see, we're adding these two integrals together because when you add these two integrals together, you're going to get the total function or the total value of the function from -1 to 4. We just have to split it up because it is a piecewise function, so it's going to be a piecewise integral. Now that we split up our integral, we're just going to take this one integral at a time, and we're going to solve the first one first, and then we'll move on to the second one. So first we're going to work on -1 to 1. We're going to do that integral first. So if you look at the function inside the integral, you'll see that technically -x is the u. But we don't have to use the U sub process in this case. We can kind of follow the easy integral process that I mentioned before, where we multiply by the derivative of the inside, or the derivative of what we would think would be our U. So first we're just going to take the antiderivative as usual of this expression. So the antiderivative of e to the negative x is going to be e to the negative x plus x, right? And then since we're multiplying by the reciprocal of the derivative, which is -1, we're actually going to get -e to the negative x plus x. So the reason why that e to the negative x has a negative sign in front of it is because we multiplied by the reciprocal of the derivative of negative x, which is -1. 1 becomes x when you take the antiderivative of it just because of the power rule. That's super simple, super straightforward. If you think about it a little bit, I don't know if you guys remember the chain rule when we were taking derivatives, but this is basically the reverse chain rule. So I don't know if that helps, but if you want to think of it like that, you can. Then we just have to plug in our values. We do not change these values because we did not use a u in this process. So we're just going to plug in our original x values, -1 and 1. That's going to give us negative e to the -1 plus 1 in parentheses minus negative e to the 1 plus 1, also in parentheses. And then all of that is going to equal negative e to the -1 plus e plus 2. Now we're going to move on to the second integral, the one that goes from 1 to 4. So that expression is going to be x plus sine pi x over 4. So we can take the antiderivative of the x very easily, right? It's the sine pi x over 4 that we're a little concerned about. So technically pi x over 4 is the u, but we're actually going to look at it as a line, and we're not going to use any u subs, and we're instead going to multiply by the reciprocal of the derivative of pi x over 4, which is 4 over pi. So our antiderivative is going to be x squared over 2. That's just the x, that's just for the x plus part. Very straightforward, power rule. And then we're going to multiply by the reciprocal of the derivative of what our u should be. So the derivative of pi x over 4 is pi over 4. The reciprocal of pi over 4 is 4 over pi. So we're going to have 4 over pi times the antiderivative of sine, which is negative cosine pi x over 4. And then we're just going to go ahead and plug in 4 and 1 into our antiderivative. So the main part of this problem is over. We figured out how to take the antiderivative of a kind of complex function without having to do a u sub. You can only really do this when you have a u that is equal to a line, because that's kind of the only way that you're able to get a numerical derivative only. So like we only get an m as our derivative for all of these, and that makes it easier for us to kind of figure out how to find the antiderivative. Anyway, so we're plugging in 4, which would give us 4 squared over 2 plus 4 pi minus 1 times -1, or times -1 times -1, minus 1/2 plus 4 pi times negative square root of 2 over 2. And now all you have to do is add those two values together. I'm going to go ahead and simplify it, our answer, and it is a little bit of a complicated process. If you don't want to simplify it and your teacher or grader or whoever you're doing this worksheet for doesn't want you to simplify or doesn't ask you to simplify, you don't have to. But I'm just going to go ahead and do it just in case anybody needs it. It is a little complicated though. So now that we're adding the two together, we're going to get negative e to the -1 plus e plus 2. That one's pretty straightforward, right? And then we're going to have to add the second part. So it's going to be plus, and then 4 squared over 2 is equal to 8. So I went ahead and wrote 8 here. And then -1 times -1 is equal to 1. So all we have is a 4 pi, since 1 times 4 pi is 4 pi. And then we're going to move on to our next set of parentheses. So minus 1/2 plus, and then I'm going to cancel out a 2, as you can see right there from the 4 pi and the square root of 2 over 2, to get 2 pi times negative square root 2. We're going to simplify that even more. So what we're going to do is we have our negative e to the negative 1 plus e. Those two are going to stay the same. We can't really touch those. The things that we are going to change are we're going to add the 2 and the 8 together to give us 10. And then from 10, we're going to subtract 1/2. So that means that we have to convert 10 into halves to be able to subtract fractions, right? The denominators have to be the same. So 10 is equal to 20 over 2, and then we subtract 1/2 from that, and that gives us 19 over 2. Then we have 4 over pi, and 2, or it's negative 2 times square root of 2 over pi, right? Let me move my head so we can see the equation better. But so what we have is, let's see, we talked about the 19 over 2. And now we have the things that are over pi to deal with. So as you recall, we subtracted 1/2 from 20 over 2 from 10 because there was a minus sign in front of that set of parentheses. You can kind of see it up here. There was this minus sign in front of this set of parentheses. So that means that the negative sign that is in front of square root of 2 is going to become canceled. It's going to cancel each other out. So this minus sign is going to cancel the negative sign of this. So we get a positive square root of 2. So that means that we have 4 pi plus 2 square root 2 over pi. So that's going to give us 2 pi times, in parentheses, 2 plus square root 2, because we took out a 2 pi from both of those parts of that sum. We took out a 2 pi from 4 over pi, that gives us 2, and we took out a 2 pi from 2 square root 2 over pi, which just gives us square root 2. So this is going to be your final answer right here. Negative e to the negative 1 plus e plus 19 over 2 plus 2 over pi, in parentheses, 2 plus square root 2. So U-subs are hard. They're a little complicated. You have to pay attention when you're doing them. But they are very common on AB exams, in Calc 1 in college. So you do need to know these. Our next video will be about general U-subs. We're going to have a worksheet with some multiple choice where you are not given a defined function. You're just given f of x, and you kind of have to find properties or things about that general function. I hope this video helped. Please give it a like and subscribe to our channel for more calculus videos. Thanks so much.